Bismillahirrahmanirrahim. Dear students, I am Akhtar Munir Khan and this is lecture number 17 and the course title is Calculus 1 with the course code Math 101, and we will continue the topic we have studied in our previous lecture, that is in lecture number 16, which is limit and continuity of functions. The outline is similar to the outline of the previous lecture, that is introduction and limit and continuity. So as we have studied in our previous lecture, the epsilon delta definition, or the precise definition of a limit of a function at a point, and this figure represents the relation of delta and epsilon in the definition of the limit. This definition says that whenever we have a point x0 and we are interested in finding the limit of the function, for example, let us say here this is a function, an arbitrary function represented by this curve, and we want to find the limit of this function or curve at that point, or at this point x0, then the precise definition of limit says that for every epsilon, epsilon is this is the epsilon distance from the limit L, for instance. This is our epsilon. Then for every epsilon, as we have studied the definition, whenever f of x belongs to L minus epsilon and L plus epsilon, whenever x belongs to x0 minus delta and x0 plus delta, which is this interval, then then the function value f of x will lie in this interval, which is L minus epsilon and L plus epsilon. So we will see, we will discuss it in detail in our coming slides. Now we have to find a delta for a given function f, a given limit L at that point x0 and a point x0 and epsilon greater than 0. So the main objective in applying the epsilon delta definition of a limit is that we have to search a delta value greater than 0, such that for all x within this satisfying this set of inequalities implies that f of x minus L is strictly less than epsilon. So this can be accomplished in two steps. First, we will solve this inequality to find an open interval AB containing x0 on which the inequality holds for all x not equal to x0. Now find a value delta strictly greater than 0 that places the open interval x0 minus delta, x0 plus delta centered at x0 inside the interval AB. The inequality f of x minus L absolute is strictly less than epsilon will hold for all x not equal to x0 in the delta interval. So these are the two steps, and we will understand it by solving an example. So we are given a function. Suppose the function is f of x equal to 5x minus 3. Then if we have f of x, if we find the limit at x equal to 1, then the limit at x equal to 1 is 2 because we will place 1 over here. So 5 times 1 minus 3 equals to 2. So the epsilon delta definition shows that, or implies that, f of x minus 2 absolute is strictly less than epsilon, which will give us that 0 is strictly less than x minus 1 is strictly less than epsilon by 5. Now we assume again another function which is y equals to f of x. So we consider this function f of x equal to x and assume that we are interested in finding the limit of this function at x naught. Then as we know that for this function, for corresponding to each input value, the output and input values are same because the function is defined in such a way that image is equal to pre-image. So for this purpose, if we fix an epsilon, suppose that we have selected an epsilon, then corresponding to each epsilon we can find a delta, and the delta will be less than or equal to this epsilon. For instance, if we consider, let us say for this epsilon, we can also select the delta to be equal to epsilon, but as we know that if this inequality holds for larger delta, then it will surely hold for the smaller delta as well. So that is why we have mentioned over here that for the function of f(x) equal to x, we can find that we find that 0 is strictly less than x minus x naught absolutely less than delta will guarantee that f of x minus x naught is less than epsilon whenever delta is less or equal to epsilon. So the basic reason of this condition is that as we know that f of x and x naught they are so because if we have suppose that the epsilon is equal to 1, we have selected a fixed epsilon, then corresponding to this epsilon the delta values will be equal to 1. Here x naught plus 1 and x naught minus 1, because x naught plus epsilon, here the function is defined in such a way that its image is equal to its pre-image. So this inequality f of x minus f of x naught will again less than epsilon because if this condition holds for a greater delta, then it will also hold for a smaller delta value as well. So now we consider a constant function. Then for the constant function corresponding to every epsilon greater than 0, let us say here this is a constant function k, and this is the epsilon. This is the constant function where we have added the epsilon, and here we have subtracted epsilon value. So we got these two vertical horizontal bars. So the function is embedded in this horizontal graphs of the k plus epsilon and k minus epsilon. So we have here we have to search for the delta, corresponding delta. Then the objective of this problem is to find an expression for the delta. So as we know that if we fix an epsilon as we did in the current case, then f of x minus k, which is the value of k, should be less than epsilon for any positive delta. But as we know that the function value f of x is equal to k, so k minus k is equal to 0. So 0 is less than epsilon for any delta. So here we can select for a constant function, there is no restriction on the delta. The only restriction is that delta should be at least positive or greater than, strictly greater than 0. So corresponding to every epsilon, no matter which epsilon we are selecting, the delta value, any delta value will work or will be used for this purpose. So an open interval of the radius 3 about x naught will lie inside the open interval. This is just an interval representation. Now consider another another curve which is y equals to x minus 1 absolute. So here we have, suppose we have y equals to x minus 1 absolute. So its limit at x equal to 5 is equal to 5 minus 1 absolute, which is 4 square absolute, sorry, 4 square root. So 4 square root is equals to 2 in this case. So this form, within this interval we can see that in the interval 2 to 8 the range values are lying in the 3 and 1 interval, that is 1 and 3 interval. So if the domain lies in this interval, if the domain lies in the interval 2, 5 and 8, this is the domain interval, let us say, then the range interval will be, let us say, assume this will be the corresponding interval in the range, so that whenever x will lie in this interval, then f of x will lie in this interval. So an interval containing x equal to 2, so that the function in example 5 satisfies f of x minus 4 strictly less than epsilon. So we have y equals to x square as a function, and we selected an arbitrary epsilon which is strictly greater than 0, and we are trying to find a corresponding delta at the position at the point x equal to 2. So we can see that corresponding to this epsilon, let us assume we have this is 4 minus epsilon, and intersecting y equals to x square at this point. Similarly, 4 plus epsilon is intersecting the function at this point. So we will directly draw a vertical projection to the x-axis, and similarly from this point we will draw vertical projection, and the distance, the minimum of the distance between these two projected values and 2 will be the corresponding value of delta r. That value can be used for serving as a delta in the epsilon delta definition. So in this case we have 4 minus epsilon and 4 plus epsilon. So as we know that this is smaller than 4 plus epsilon, because here epsilon is a positive number, and subtracting a positive number and adding a positive number to a same number makes this term less than this one. So we will choose this delta value, that is in this situation corresponding to any epsilon, our delta will be 4 minus epsilon square root. So now we move to a function which is defined piecewise. For instance, y equals to x divided by x absolute. This is the right branch and this is the left branch. So whenever we are trying to find the limit at x equal to 0 over here, then we can see that the limit from the right is different from the value that we have obtained whenever we will come towards 0 from the left. That is, whenever we are coming towards 0 from the left, then the function values will approach to minus 1. On the other hand, whenever we will come towards 0 from the right, then the function values will approach to plus 1. So we have another representation of the left and right. We are describing these one-sided limits. Suppose that we have a function f of x, and we are trying to find the right limit at x equal to c. Then this will be denoted by limit x approaches to c from the right, f of x equals to L, and this will mean that we are coming towards c from those values which are strictly greater than this value c. And we can see that whenever we are approaching towards c from the right, so here the function value comes or approaches to this value L. On the other hand, if we are approaching towards c from the left, then the function limit can be seen to be approaching to our value m. So this will be the left limit or left hand limit, and this will be the right hand limit as x approaches to c. So in this situation, suppose we are interested in finding the limit x approaches to 2 from the left, then from the left we have this is our x equals to 2, and if we are coming from the left, then one can see that the limit at this value is 4 minus 2 square to 0. And if we are going to define the limit from the right, then as there are the domain, there is no values of the function defined for greater than 2. In this situation, we cannot come from the right hand side. So that is why sometimes both sided limit does not work and only one sided limit carries meaning. So that is why we are considering left and right limits. So here, but for minus 2 we can define a right hand limit but cannot define left hand limit, and the right hand limit again can be seen from graphically and using mathematical calculation that their limit is equal to 0. So a function f of x has a limit as x approaches to c if and only if it has left hand and right hand limit there, and these one-sided limits are equal. So a function has a limit as x approaches to c, that is, we will say that a function limit is L whenever both from left and right we are approaching only to this number. Then after that we will say that the function limit exists at this point c. Whenever from both directions we are coming towards c, we get the same value, then we will say that the function limit exists. So consider this graph. So here one can see that the limit exists only for 3. Here the limit is equal to 2, but here the limit is equal to 1 for 2, because whenever we are approaching to, although exact value of the function at x equal to 2 is 2, but whenever we are approaching towards 2 from the both the sides, so the limit of the function value is approaching to 1, and similar is the case for other values. So right hand limit and left hand limits in terms of the epsilon and delta. We say that f of x is a right hand limit L at x naught, and we write limit x approaches to x naught from the right, f of x equal to L if for every epsilon greater than 0 there exists a corresponding delta greater than 0, such that for all values lying to the right of the x naught and the left and lie to the left of the x naught plus delta, that implies f of x minus L absolute is strictly less than epsilon. And we say that f has a left hand limit L at x naught and right limit x approaches to x naught from the left, f of x equals to L if for all values that are lying to the left of x naught and to the right of x naught minus delta, which implies that f of x minus L is strictly less than epsilon. So this is the figure for one-sided limits. Suppose that we say that a function limit exists, right hand limit exists. So for all values From the right, we are coming from the right, so this is the definition for the epsilon delta definition for the right hand limit. So for all values of x that lies in the interval x naught and x naught plus delta, then the function values will be lying in the epsilon neighborhood or epsilon interval about this value L. Similarly, if we consider the left hand limit, then for all values corresponding to each epsilon, we can find a delta, so that whenever x naught minus delta, whenever x will lie in this interval, that is for left hand limit, x values which are arbitrary and x naught is fixed, then all these x's will lie to the left of this x naught and to the right of x naught minus delta. On the other hand, function's value will be lying within this range, then we will say that the left hand limit at this point is equals to L. So the restriction or the difference between two-sided limit and one-sided limit is that here we fix x naught and take and add or subtract a delta value to the one of the endpoints, but in double or in a two-sided limit, we add and subtract x naught delta from x naught from both endpoints. So this is the epsilon delta definition of the one-sided limits. Now assume that we have a function f of x equals to x under the root. Then as we know that for the square root function, the domain consists of only non-negative numbers, that is those numbers which are greater or equal to 0 will constitute the domain of this function. So as we know that the lower bound of the domain of this function is 0, and if someone is going to find the limit or trying to find the limit at this point x equals 0, then we will use the one-sided limit, because there is no function values, because the domain consists of only, or the function is defined only for the right side of the function of the x equals to 0. So for this purpose we will use only those values which are lying to the left of the x equal to 0. Now as we know that the limit at this function value is at this x equal to 0 is 0, so we denote it L, we denote it by L, and L is equal to 0 at x equal to 0 for this function x under the root. Now suppose we have chosen an epsilon which is strictly greater than 0, a positive real number. Then using some mathematical calculations, we can show that the delta value is equal to epsilon square. Note that in epsilon delta definition, the delta will depends on the epsilon. So here delta is equal to epsilon square. So that means that whenever we are approaches towards 0 from the right, then the function limit value, the function approaches to the limit x equal to 0 is 0. Now we consider another function y equals to sine 1 by x, and we are trying to investigate the limit of this function at x equal to 0. So if we see that if we put here x equal to or x approaches to infinity, then the limit will be undefined, because there will be as from the behavior of the function here x equal to 0 shows that the oscillation of this function increasing as we move towards 0 from both the sides. So it means that there is no fixed value for the limit of the function, that is the function oscillation increases So that is why at x equals to 0, at x equals to 0, the function is undefined. That is, we are trying to find the limit at x equal to 0, not at x equal to infinity. So this is the limit of the function, trigonometric function. Now we consider another function, sine theta by theta, where theta is in radians. So from the graph, it is very clear that as we move away from theta equal to 0, then this limit goes to 0, and as we move towards 0 from both the sides, then the function graph shows that its limiting value is equal to 1. So the graph of this is the graph of f of theta, which is equal to sine theta divided by theta. So using the fact in the previous figure, so we conclude that limit theta approaches to 0, sine theta by theta equals to 1, where theta is in radians. This is an important theorem and an important result. We will frequently use it in various calculations in the coming lectures. Now we move to the limit at infinities, that is limit at plus infinity and minus infinity. We say that f of x has the limit L as x approaches to infinity, and write limit x approaches to infinity f of x equals to L if for every epsilon greater than 0, strictly greater than 0, there exists a corresponding number m such that for all x, whenever x strictly greater than m, implies that f of x minus L is strictly less than epsilon. And similarly, we say that f of x has the limit L as x approaches to minus infinity, and we write limit x approaches to minus infinity f of x equals to L if for every epsilon strictly greater than 0, there exists a corresponding number n such that for all x strictly less than this capital N, we have that f of x minus L is strictly less than epsilon. We will show these two definitions by a geometric interpretation. We will give a geometric interpretation to these two definitions. Suppose that we have a function which is the rectangular hyperbola y equals to 1 over x. So for this function, as we move towards the plus infinity, then the graph as can be seen in the figure that it approaches to 0. Its graph tends towards 0 whenever x approaches to infinity. Similar is the case whenever x approaches to minus infinity, then the graph still goes towards 0. So this is a geometric approach towards the problem. Now we are trying to understand the previous definitions using this geometric interpretation. Suppose we have y equals to epsilon, then for this situation, so no matter what positive epsilon is, the graph enters this band at x equals to 1 over epsilon and stays within this rectangular box. That is, suppose we have selected y equals to, suppose we have selected an epsilon, then corresponding to this epsilon, we can find a number m. Here in this situation, it is equal to 1 over epsilon, such that for all values larger than this m, the function value will lie below y equals to epsilon. That is, it will remain in the box for all values of x strictly greater than this m. Similar is the situation whenever we are trying to approach towards minus infinity. then no matter what positive number epsilon is, the graph enters these bands at x equals to -1 over epsilon and stays within this rectangular box. Suppose we have selected minus epsilon, then we can see that for all values of x which are strictly less than n, then the function value will be lying above the y equals to minus epsilon. So this is the geometry behind the limit at infinities. So there are some results or theorems, limit laws as x approaches to plus minus infinity. If L, M and K are real numbers and limit x approaches to plus minus infinity, f of x equals to L, and limit x approaches to plus minus infinity, g of x equals to m, then the sum rule states that the limit of the sum is equal to the sum of the limits. Similarly, the difference rule states that the difference of the limit of the difference of two functions is equal to the difference of the limits of these functions. The product rule states that the limit at plus minus infinity of the product of the two functions is equal to the product of their limits, and these are other rules that we have studied for the limit at finite values. So they are all similar. So now we move to the application of the limit of function at infinity, which leads to the asymptotes of a function. So asymptotes will be defined in this way. A line y equals to b is said to be the horizontal asymptote of the graph of a function y equals to f of x if either limit x approaches to infinity, f of x equals to b, or limit x approaches to minus infinity, f of x equals to b. So this horizontal line, as we know that y equals to a constant, gives us a horizontal line, that is a line parallel to x-axis. So this line will be called horizontal asymptote if at least one of this condition is true. Consider this function y equals to 5x square plus 8x minus 3 divided by 3x square plus 2. And then the line y equals to 5 by 3 is the horizontal asymptote of this function, because we can find that limit x approaches to infinity, y, that is taking the limit as x tends to infinity of this function, will give us this value 5 by 3. So that is why we say that y equals to 5 by 3 is a horizontal asymptote of this function. Now consider another situation. Let us assume we have a function y equals to 11x plus 2 divided by 2x cube minus 1. And then taking limit as x tends to infinity. So in this case we will get the limit to be equals to y equals to 0 whenever x approaches to infinity, and in this fashion we will say that y equals to 0, which is the x-axis, is the horizontal asymptote of this function. The graph of the function in example 9, the graph approaches the x-axis as x absolute increases, that is the graph approaches to 0, in other words, as x absolute is increasing, that is whenever we are enlarging the x in both the sides or from both the sides, then the graphs will decline towards the x-axis, which is y equals to 0. So now consider another example. So suppose that y equals to 2 plus sine x by x, then whenever x approaches to infinity, then sine x by x will give us the value. This term will be vanishing, and in this fashion y equals to 2 is the horizontal asymptote of this function. But this asymptote is of special interest due to the fact that the asymptote macros is one of its asymptotes infinitely often. That is, it is not necessary that the asymptote will only it will only uh, it will be only approaching to the curve, or it may be it may intersect the curve in different points. It is not necessary that every asymptote will be like a tangent to the curve at infinity. So this is a special asymptote, or we can give to this case a special attention, because here y equals to 2, we can see that this asymptote is intersecting the function at different points, or even infinitely often. So this is a special example. Now the function in this situation, we have other asymptote, which is called the horizontal oblique asymptote or vertical asymptote. So this is the oblique asymptote, an asymptote which is neither horizontal and nor vertical, is called oblique asymptote, and the asymptote to a function or to a curve such that it's parallel to y-axis is called vertical asymptote. So here in this case, you can get as high as you want by taking x close enough to 0, no matter how high b is. The graph goes higher, that is y equals to 1 over x. So as we move towards 0, then the graph will going in the upward direction. Similarly, as we move towards x equals to 0 from the left, then you can get as low as you want by taking x close enough to 0. So these are the one-sided limits. So in this case, note that whenever we approach to x towards 0 from the right, then the function goes to plus infinity. On the other hand, if we move towards 0 from the left, then the function goes towards minus infinity. So consider another example, y equals to 1 divided by x minus 1. Then as we move towards 1 from the right, that is limit x approaches to 1, y, then this limit will give us infinity, plus infinity. So near x equal to 1, the function behaves the way the function y1 over x behaves. So near x equals to 0, its graph is the graph of y equals to 1 over x shifted 1 unit to the right. So this graph is obtained from the y equals to 1 over x by shifting the whole graph of the rectangular hyperbola 1 unit to the right. So as it is a horizontal shift, where we have subtracted 1 from the x, so that will move directly the function to the right of the original function. So as we can plot that the overall graph of the function was somewhat like this, but when we have subtracted 1 over here, so the graph moved to the right of this function 1 unit. So note that here x equal to 1 is the vertical asymptote, because limit x approaches to a, that is limit x approaches to A, uh, limit x approaches to A, y was or f is equals to plus infinity, which is the definition of the vertical asymptote. So this line x equal to A, so here A is 1, is the vertical asymptote of this function. So the graphs here, consider this example y equals to 1 over x square. So no matter how high b is, the graph goes higher. So this is the graph of 1 over x square. So note that the difference between 1 over x and 1 over x square, in 1 over x, one branch of the rectangular hyperbola was negative and the other was positive. That is, one was lying in the first quadrant and the other was lying in the third quadrant. But in this case, both the branches of that rectangular hyperbola will be lying above the x-axis, or that is, both will lie above the x-axis, or one will lie in the first quadrant and the other will lie in the second quadrant. So the graphs of the function in example 2a, f of x approaches infinity as x approaches to 0, and in b, g of x approaches infinity as x approaches to minus 3. So we can say in both the cases that x equals to minus 3 and x equal to 0 is the vertical asymptote of this function. For this function, x equal to 0 is the vertical asymptote, and for this function, x equals to minus 3 is the vertical asymptote. So we say that f of x approaches to infinity as x approaches to x naught, and write x approaches to x naught f of x equals to infinity if for every positive real number b there exists a corresponding delta strictly greater than 0, such that for all x, whenever x is satisfying this inequality, the set of inequality, because these are two inequalities, then this will imply that f of x is greater than b, and similarly for minus infinity, f of x should be less than minus b whenever x satisfies these inequalities. So this is the geometric interpretation of the previous example, of the previous definition. So y equals to, for x naught minus delta, that is x lying between these two endpoints, the graph of f of x lie above the line y equals to b. Similarly, for whenever we are taking limit at minus infinity, when the function approaches towards minus infinity, whenever x approaches to some x naught, then this will be equivalent to say that x naught minus delta is strictly less than x, is strictly less than x naught plus delta. The graph of f of x lie below the line y equals to minus b. So here we can see that whenever x lying in this region, then that is sorry in this region, then function values will lie below this minus b. So this is the infinite limit whenever x approaches to x naught and f approaches to minus infinity. So a line x equals to a is said to be the vertical asymptote of the graph of a function y equals to f of x if either of these two conditions is satisfied. The condition is that limit x approaches to a, f of x is equals to plus r minus infinity. If this condition is satisfied or this condition is satisfied, then we will categorize x equals to a, where x equals to a is a vertical line, is the vertical asymptote of this function y equals to f of x. So vertical asymptote has the property that whenever you are approaching uh, at the larger end, you can say that one can say that at infinity, the vertical asymptote or the asymptote will touch the curve at the infinity. At infinity, this curve and the asymptote is the line which will intersect or which will touch the corresponding curve at infinity. For example, we have seen the example of y equals to 1 over x. So here we saw that the line x equal to 0 was touching this function y equals to 1 over x at infinity. So, but mathematically, the mathematical formulation or the mathematical trick to find whether or not a vertical asymptote exists for a function. So, we will have to check for those values in the domain where to which v approaches x and the limit goes towards plus or minus infinity. So this is the trick behind the vertical asymptote. So here is the two vertical asymptote. This is the vertical asymptote x equals to 0 because whenever we approach x towards 0, then our function goes towards infinity. Horizontal asymptote is a bit different. It is the line where the function whenever x approaches to infinity, the limit at infinity of a function will be called the horizontal asymptote of that function, and the limit at a point where the function approaches to infinity will be called the vertical asymptote of that function. So these are this is the vertical asymptote for this function, and this y equals to 1 is the horizontal asymptote of this function. So this is a function y equals to minus 8 divided by x square minus 4. So one can see that whenever we are approaching x towards 2, then we will get y equals to vertical asymptote, then y will approaches towards minus infinity. It can be seen over here. For instance, I'm putting x equals to 2, then minus 8 divided by 2 square, which is 4 minus 4. So surely something divided by 0 equals to infinity. So it means that the limit of the function at this point goes to infinity. So a line parallel to y-axis and passing through this point will be the vertical asymptote of this function. And on the other hand, the line whenever x approaches to infinity, then the function limit at infinity. Here, if we approach x approaches to infinity, then 8 divided by infinity minus 4. So we will get limit value equals to 0. So this value or the line whose equation is the limit at infinity of this function will be the horizontal asymptote. So here are some trigonometric functions, for instance, tangent x. So as we know that the odd multiple of pi by 2, whenever we are putting the odd multiple of the pi by 2 in the tangent, then the tangent will give us the value infinity. Or in other words, whenever x approaches to the odd multiples of pi by 2, then the graph approaches to infinity. So that odd multiple will constitute the vertical asymptote of this function. This is the vertical asymptote of this function. So these are some vertical asymptotes of the tangent functions, and these are the vertical asymptotes of the secant function. So the graph of secant x have infinitely many vertical asymptotes. So it's not necessary that there is a finite number of asymptotes, vertical or horizontal. It may be more than one or even infinitely many vertical asymptotes exist for functions. This is the asymptotes, vertical asymptotes for the tangent x. Now there are some other sort of asymptotes which are known as oblique asymptotes. So we can find, we can also define another type of asymptote which is oblique asymptote. So consider this example, y equals to x square minus 3 divided by 2x minus 4. So after factorization or dividing numerator by denominator, so we got this result. Now consider the graph of this function, which is the blue arrow. Here on both the sides we have plotted both branches of this hyperbola. Now we can see that whenever x approaches to 2, for instance, just put 2 over here, so we can see that the limit of the function goes towards plus and minus infinity. So at this point x equals to 2 will be the vertical asymptote, but observe that the graph is although not going towards 0 as x approaches to infinity, but we can find another line uh, such that the vertical distance between the curve and the line goes to 0 as x approaches to infinity. For instance, we factorized this fraction and we got this expression. Now approach limit x tends to infinity, or put x tends to infinity in this expression, so we will get x by 2 plus 1. That is, if we put if we take the limit as x tends to infinity of this term, then this term will be vanished and we will be left with only this expression, which is an expression for a horizontal line, and this is the graph of horizontal line which touches this graph at infinity. So we can see that this line is neither vertical nor horizontal. So other than horizontal or vertical line, if there is an asymptote, then that asymptote will be categorized as oblique asymptote. So this asymptote is neither horizontal nor vertical. So that is why it is called the oblique asymptote for this function. So overall we got two asymptotes. One is vertical and the other is oblique asymptote. Now we move to the definition of the continuity at a point. Suppose we have a function y equals to f of x, then the function f of x is continuous at an interior point C of its domain. The interior point means the point that is not the end point of the interval of the domain interval. Then this point is in between the two endpoints of the domain. The domain may be a closed interval, half closed, half open interval. So interior point is in the middle of, or even in the interior of the interval. So at that point x equals to c, where c is an interior point, the function is said to be continuous at this point if this condition holds true, that limit x approaches to c, f of x equals to f of c, where f of c is obtained by directly substituting c in the function, and this is the limiting value of the function as x approaches to c. So if these two values are same and are finite, then we will say that the function is continuous at this point. So the continuity of the function at the end point states that a function is continuous at a left end point A, or is continuous at a right point A, right end point B of its domain, if limit x approaches to A from the right f of x is equals to f of a, or limit x approaches to b from the left, f of x is equals to b respectively, f of b respectively. Now we see what do we mean by these definitions. So we have suppose a function which is the upper branch of the circle, whose equation is y square plus x square equals to 4. So this represents a function, and we can see that there are no gaps or holes in the function. So the function looks like a continuous function, that is, it is continuous everywhere in the prescribed domain, which is -2 and 2. Now suppose another function which is the step function. So look at the graph whenever x equals 0. So at x equals to 0, we can see that from the left the function is equal to 0. That is, from the left, or to the left of the point x equals to 0, the expression is y equals to 0, and there is an abrupt change in the value at the point just right just to the right of the function. That is, we can see that if we take the limit of this function, then we can see that the limit, left limit is 0 and right limit is 1, and left limit and right limit are not equal. Further, f of 0 is equals to 1, which is defined or shown here. So from the previous definition, we can see that the limiting value is not equal to the direct value, which is equals to 1. So it means that the function at this point is not continuous, and it can also be seen graphically that there is a vertical gap between the values of the function. So continuity test. So there is some steps how to check whether a function is continuous at certain point. So we see these steps in the following test. So suppose we have a function f of x, then the function is continuous at this point x equals c if and only if it meets the following three conditions. The first condition is that f of c must exist and is finite. C lies in the domain of f, that is, c is a point in the domain of the function. The second condition is that limit at this point x at c should exist. So the existence of the limit means that left limit and right limit should be equal. And the third and most important condition is that the limiting value we obtained in step 2 should be equal to the value we got in step 1. So if these three conditions meets, then we say that the function is continuous at C. So suppose we have the integer function, or the step, and the floor function. So the graph of the floor function is defined by this, and it can be defined as the greatest integer less or equal to x. So for instance, for the interval including 0 and excluding 1, so this integer function will give us, this floor function will give us 0, and for 1 to 2, excluding 1 and including 2, including 1 and excluding 2, the function gives us 1. So this is just like steps. So this function is discontinuous at each integral value. So we can see there are horizontal gaps at all the integer values in the domain. So we can see that the function has infinitely many discontinuities. Suppose we have some other functions which are shown in this figure from a to d, a to f. So we can see that the first function a is continuous everywhere. Here it is discontinuous at only one point, which is x equal to c, because there is a empty hole or empty space between the function and here is the function is still discontinuous because there is a empty hole, and this is also discontinuous because there is a vertical gap, so due to which the function lost its continuity. Here the function is again discontinuous as it approaches to infinity, and this is also a discontinuous function because here the limit does not exist at x equals to 0. So in short, we can say that the function in the example in the figure A is continuous and all others are discontinuous. Now we move to a very simple example which we used frequently, which is a rectangular hyperbolic function y equals to 1 over x. So here the function is again discontinuous at x equals to 0 because the limit approaches to infinity. So it means that the limit at x equals to 0 is not finite. So the properties of the continuous function are similar to that of the limits conditions or properties. Now we use the composites of the continuous function are continuous, which is a very important result. So this result says that if a function is continuous at C, if f is continuous at C and g is continuous at f of C, then G circle f, the composition of G and f, will also be continuous at x equals to C. So this result is frequently used in proving theorems, mathematical theorems or mathematical results in advanced courses. So, here we are not going into the detail of this theorem, but just to revise or remember that whenever a function is f is continuous at C and g is continuous at f of C, which is the image of C under f, and f of C is the pre-image of this function g, then the composite function of g and f will also be continuous at x equals to C. So composite of the continuous function, so this is the theorem in its formal words. So this is the graph of the continuous function. Now it is not necessary that a function will remain always discontinuous. Sometimes it is also possible to make a discontinuous function as continuous by doing some modifications or providing some points to the function in the range. Now suppose the function sine x by x, then this function is discontinuous at x equals to 0. The reason is that the direct putting value f of 0 will give us the 0 by 0 form that will create an empty hole between or in between the function. So here this is an empty hole, so it means the function is discontinuous at this point, and all other points other than these the function is continuous everywhere. So to remove this discontinuity, we are supplying a value at 0, we are making it equal to 1. So this will be called the continuous extension of the discontinuous function. For instance, the graph of A, which is here, which is this one, is the graph of the function f of x equals to sine x by x, where x is lying between minus pi by 2 and plus pi by 2. So it does not include the point 0 and 1 as we discussed the reason. Now because the function is not defined at x equals 0, but we can remove the discontinuity from the graph by defining the new function are making some modification in the old function, and we denote it by f of x with f of 0 equals to 1 and f of x equals to f of x everywhere. Note that f of 0 is now equals to limit x approaches to 0 f of x. That is the limiting value, which is 1, we have supplied, or we have added to the old function, and that will fill this gap. So such sort of discontinuities are called removable discontinuities. So here is another other cases. So there are also removable discontinuities in the function, so we can make them continuous. And these are the references from which we have included the slides material. So thank you very much.